Morning, guys. I'm just setting up my screen right now.
Good morning.
Good morning. How are you? How is everyone?
Good. How are you?
I'm good. I'm good. I had some coffee and feeling better. Hi, Queenie. Hi, Matthew. Hi, Peniela, Ishan, Michael, Raymond. Raymond, were you not there for the past few days? Unmute.
Yeah, I wasn't there Tuesday.
Oh,
I wasn't there Tuesday, but Thursday I was.
okay. Okay. You're doing all right?
Yeah,
Cool. Danielle, Saisha. Isha, I haven't seen you. Are you okay? Is everything all right?
Yeah, I'm good. How are you?
You don't sound good. Okay, we can talk offline. Hi, Willis. Hi, Peyton. Hi, Crystal. Hi, Carly with a K. Hi, Kevin. Brandon, Desiree, Craig, Henry, Sergio, Drake, Karina with a K, Lupita. Okay, we're going to talk about double bonds. When does Isha? When does vet school start in Davis? September or August?
I think August because the white coat ceremony is in August.
White goat ceremony. White goat ceremony. It should be. You are a vet. It should be a white coat. It should be white goat. You'll be like walking in front of a procession of like 50,000 white goats. That sounds
That
good.
would be something.
Huh?
Yeah. I said that would be something.
I don't want to crack any too inappropriate jokes in the morning. Yeah. All right, 26 of us. That could be the name of the store. We have already wasted a minute. Let's go to the board. The beautiful board. Oh, okay. I love you, my board. Okay, all right. No more bad jokes. Okay. I got brand new pens today, so that's something to be excited about. Well, the black has few miles on it, but the rest are new. That doesn't belong here. All right, so we are who we are. We are the chemators. That's not chem, it's Ken. And today is, I have no idea. 4th? Yes. Today is 4th. March the 4th. We are talking about alkenes. Okay, alkenes must have at least one double bond. It's a hydrocarbon with at least one double bond. A few facts that I want to just mention. We talked about, I'm just going to do like a 5-minute review. Okay, my 5 minutes are usually 15 minutes, but let's see if I can do it today in 5 minutes. So alkane, what have we learned? A very quick review. What have we learned about alkanes? Alkanes only have single bonds, nothing else. Only single bonds. Okay. Just some general like random bullet points. Okay. Random bullet point number 1. When we see something like this, now since you have been in this class for a while, what's the while? Half of January, 1/3 of January and February. Yeah, little over a month and a half, or month and quarter, something like that. When you hear methane, you should be thinking about a stinky gas. You should be thinking about CH4. That's if you're a general chemistry student. If you're an organic chemistry student, The moment you hear methane, you should be thinking about a cube, and you're in the middle of the cube, and there are two guys there and two people there. Okay, you're making a tetrahedral shape. So you should be thinking about a molecule that's got some depth. It's not a two-dimensional molecule. Carbon and four hydrogens equally spaced around that carbon, like with four bonds. And you can think about, feel free to think about four bar magnets connected in the center at their north poles or south poles, and they're sticking out to be as far away from each other. That's the image that should pop in your brain. So we see something like this, we think about something like that. That's the image that pops out first. Then we think about something like this. Okay. And what else comes to our mind? Well, we think about, this is in excited state first, ground state, excited state, hybridized state. Okay. What kind of hybridization? The pens are brand new, so I think they need to be kind of run for a while. sp3 hybridization, we will get to that. That's very critical. We also know that the bond angles are 109.5 degrees for methane. What else do we know? If I ask you, what's the makeup of this bond? We talked about it. It's this particular bond is made from hydrogen's 1s orbital and carbon's sp3 orbital. That's the makeup. Okay, that's what this bond is made out of. What kind of overlap is there? What kind of bond is it? Well, it's a covalent bond. We all know that. These bonds are covalent. What is a covalent bond? Covalent bond happens by sharing two electrons. Two electrons shared. I actually screwed up a question in Chem 128A. I realized it much later. I picked a wrong element to write a question. It should have been aluminum chloride. But I thought, you know what? If I put chlorine and ask my students to write down the electronic configuration, they have to go through the D shell. I don't want them to deal with that. I want to keep it simple. So I changed it from chlorine to fluorine. And I screwed up. I didn't realize that when I'm picking fluorine, it's very electronegative, and that bond is not covalent anymore. It's an ionic bond. So that was a big boo-boo. So I'm trying to figure out like how to solve the problem right now, how to deliver the message to my Chem 128A students without looking like a total idiot. So I'm cooking up some stories. No, I'm not cooking up some stories. I'm going to tell them that I made a mistake, but I'm going to turn it into a bonus question. I'll say, what do you guys think your instructor did? Can you guys point out what the problem is? Then I'll give you 3 bonus points, something like that. So we all make mistakes. So 2 electrons shared. 2 electrons shared. We're going to talk about something after we complete the alkene discussion, like the bond properties going a little bit deeper. Okay. 3 electrons shared. The 2 electrons shared don't have to be equally shared. If it is equally shared, then it's nonpolar. If it is pushed toward one end because one element is more greedy for the bonded electrons, then it's a polar covalent bond. Okay, we learned that. Okay. How are these bonds made? These bonds are made by axial overlap. That's important. Okay, what I'm running out of colors. That's fine. So these bonds are called sigma bonds. Sigma bonds happen by axial overlap of orbitals or orbitals. I have no idea what the right pronunciation is. Okay, so bits and pieces of information. Alkanes, only single bonds. The smallest alkane, methane, it looks like that. This is 2D. This is 3D. And some facts about alkane. It's sp3 hybridized. You should think about what that means. 109.5 degrees. This bond is made from 1s and sp3 orbital. Okay, this is critical. I might throw a question with that in there. Okay, I might ask you, what's the makeup of this bond? 1s sp3. What else? It's a shared bond, covalent bond, slightly polar, not very polar. We will talk about some definitions. Then this bond, whenever you see a sigma bond, whenever you see a single bond, it's a sigma bond. Why is it called a sigma bond? It's axial overlap. Okay, so think about that. Okay, now we're going to go to the next contender, not methane but ethane. What does ethane look like? Ethane looks like this. This is ethane. We discussed it because ethane was the father of ethene. We didn't talk about naming alkenes. From ethane comes the smallest alkene, the atom of alkenes. Okay. Let me ask you a question. Think before you answer. Think for like half a minute. Question. We discussed it in the previous class. Try to answer quickly, but after giving it some thought. What is the makeup of the CC single bond? What is that bond made out of? What kind of electrons sitting in what kind of orbitals? Anybody?
That's a.
Was that an answer, or was that you're just thinking out loud? What is, so this is sp3 1s, sp3 1s. What is that bond made out of? What kind of electrons? Where are they sitting in? Somebody? Anybody?
sp3.
Who said that? Peyton. Perfect. Perfect answer. sp3, sp3. Just take one other random bond. How about this bond? Somebody else or anybody? What's this bond made out of?
1s sp3.
1s sp3. Okay, good. Review over. 10 minutes, 9 minutes. Not too bad. Not 15 minutes. Sounds good? Can we stick something here? Let's see. Okay. Let's draw the alkene, then we're going to erase the board, take a picture, erase the board, and go to the fresh empty canvas. Okay. From here, this guy is called ethane with a big A. It's important because that A indicates alkane. Okay. Now you will realize that naming alkene can be very simple, very easy. Okay. So from here, you can think about, and this guy is C2H6 falls under CnH2n plus 2 rule. All alkanes. When we make our first alkene, okay, the bottom line is there has to be a double bond. Okay, so in order for you to have a double bond, there has to be at least 2 carbons. So the 2 carbon guy is the smallest alkene. Okay, I'm going to put the second bond in red color. The red is still not writing very well, so I'm overwriting. Okay, so We will talk about its shape in a second. This is the smallest alkene possible, okay? First alkene. Smallest alkene. Okay, smallest alkene. If you say that this is carbon 1 and carbon 2, this is carbon 1 and carbon 2, you can tell that it lost some mass. It lost a couple of hydrogens because it wanted to make that bond. Okay, so if these are the electrons from carbon 1, if these are the electrons from carbon 2, and if these are the electrons from hydrogens, okay, something happened here. Well, it's got this guy here, this electron here, that electron here, but it needs to use one more electron to make that second bond of the double bond. That's important. Excuse me. So hydrogens are pretty much the same. Okay. Again, except for that second part of the double bond, all the rest of the bonds are like normal bonds. Nothing funny going on about that. Okay. So these bonds are all sigma, 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 and sigma. That red bond is the sketchy area, is a little weak point, and that's a pi bond. We discussed it in the past, in the last class on Tuesday. That's the pi bond. We also discussed its hybridization. We just got to the hybridization discussion. We're going to go through that one more time. So this is still a review. Well, 15 minutes. Yeah, 15 minutes. It can save you a lot of pain and agony. Okay. So that's ethene. That's the smallest alkene with a double bond. And remember, the double bond is a mixture of a sigma bond and a pi bond. Remember that. I'll pause for 15 seconds. This whole thing is the double bond, right? This is the double bond. The green is pretty bad. This whole thing is the double bond, sigma plus pi. Triple bond will be sigma plus pi plus pi. Let's not worry about it right now. So one question in the next quiz could be, how many sigma bonds are present in the smallest alkene? Draw the smallest alkene. Well, if it were a free response question, it's not going to be that way for you guys. So if I have this structure drawn in one color, let's say I just put this guy. One question could be number of pi bonds, number of sigma bonds, number of pi bonds. Okay. So how many sigma bonds are present in the smallest alkene? Count.
1.
What did I say? Pi. Okay, sorry. I wanted to say sigma. I'm messing it up. Sorry. How many sigma bonds are present in the smallest alkene? 5. How many pi bonds are present in this molecule? Got it? Everybody's with the force, with the double bond. I don't think I have any more space, so I think this is review, fast review, and let me take a snapshot, and we will go from here. Sorry, I'm going to block the camera again. I can pause for like few seconds.
I had a quick question.
Absolutely.
So on a test, if we were asked to draw the smallest alkene and you wanted us to draw out the electrons too, do we have to draw it like that example right there with the open circles and the closed circles?
I won't be asked. It's primarily going to be multiple choice. I don't know when. Sometime I might throw like a 1 page of free response questions. So it's not going to be, I'm not going to be asking you to draw, but if I asked you to draw, so Peyton, are you asking, if I ask you to draw the smallest alkene, should you draw it this way or should you draw it that way? Is that your question?
No. So when you asked to draw it, like the one on the right with all the colors, yeah. If we were like, if you had 4 multiple choices up and some of them were all closed dots and some of them, half of them were like open dots, does that,
Oh,
is it-
closed dots or open dots, it really doesn't matter.
okay.
So yeah. That doesn't matter. So I use different shapes. You know, if you go to a book, I don't think the book will ever. I haven't looked at the book in a long time. My bad. Okay. I'm using a closed dot to represent that this electron is coming from carbon on the left side. An
Okay.
open circle, I'm just trying to use a different shape to designate that particular electrode is coming from carbon number 2. And blue dots are coming from blue hydrogens, just to kind of distinguish between the different types of elements. So
Okay.
that's all. I mean, this is totally fine too. If I ask you to draw the, what is that called? Lewis dot structure of the smallest alkene, you could just do this. Easiest way. That's
Okay.
fine. That's totally fine. If you want to do it cross circle and a square for the hydrogens, it's just a representation. It's just a symbol. Electrons are not round or solid dots. Who knows what the electrons look like, right? It's just a negative charge. So any shape is fine. You can use the same shape. You can use different shapes. Let your imagination fly through the roof, whatever you come up with. You can use like a, exclamation sign. You can use a diamond. I don't know, a pentagon if you have time. You can put like a star. Let your imagination fly. I keep seeing, I keep telling my students, especially in 128 A and B, that so they were all free response questions, and I'm still struggling to finish grading. It's just taking me an enormous amount of time. I'm thinking about cheating in the next exam by making it a multiple choice question, which is not recommended for those 2 classes. So I keep telling them that sometimes I have like question 3, write down the electronic configuration of any 2 of the elements, okay, or whatever ions. Then I have lithium plus, beryllium plus plus, and ammonium, NH4 plus. They're supposed to do any 2. And I know that some of my students are going to be very upset because I told them that do not answer more than what is necessary. So here is the deal. I mean, if you're supposed to answer any 2 and you're confident about 2, 1 and 3, your concept is a little sketchy about number 2. But if you are not thinking, or you are just on this kind of a journey that I'm going to look at every take every scenic route, and I'm going to look at everything, and I'm going to answer everything. And if you answer 3 of them without thinking, or thinking that, oh, my instructor might be impressed that I actually tried everything. But if you make mistake in 1 of them, and if you expect me to like ignore it, I'm not going to do that. So if you answer more than what is necessary, and if you make a mistake, I'm going to take points off, because wrong is wrong. So I don't think it pertains to you guys that much, but if it does, then realize that sometimes you're just supposed to do what you have been asked to do. Don't do more than what is necessary. If you see like a multiple choice free response question in test 2, whenever that happens. And if you are only supposed to answer 3 out of 5, answer 3 out of 5, unless you are really, really confident you have nothing better to do that morning. If you are really bored and you're like, I think I'm going to just spend time answering the 2 other questions, but be careful that even if 3 of your answers are perfectly correct and you should get full points, if you did the 2 extra questions and you made mistakes, I'm going to take points off, because wrong is wrong. Okay, keep that in mind. It's not so important for you guys, but then I'm expecting some backlash from at least from 128A students whenever all my grading is done. Okay, so Peyton, are you okay with my answer? Any shape is fine.
Yeah, thank you.
If you are doing a pre-response, I would just put the darn dots, not spend time. Or this is what I would do. If I ask you to do methane, I would draw this. If you draw that, I'm going to take points off, because again, Chem 128 students did that. They didn't put the dots, and they're supposed to put the dots. The easiest way, if you're running out of time, I would just cut it. That's my electron. I don't care how the electron is shown. Okay, I just draw the bond and cut it. Cut means there is an electron here and an electron here, electron here. So it's kind of like cross. Okay, so do not spend too much time. I'm also seeing like some tendencies in my 128A and B students. They're using like making it like a piece of art, like multiple colors. Somebody used 7 colors in the test 1. Can you believe that? The 4 standard colors, like what I use, and then they had pink and magenta and some weird color, like a highlighting color, like a yellow color. Like, do you really have so much time? And obviously make some mistakes. Okay, that's my frustration. So don't try to be try to make your answer look like a piece of art if there is a pre-response down the road. I'm thinking about doing maybe next test. Next quiz will be like simple, multiple choice. Next test, maybe there will be 1 page of free response. Okay, simple. So that's that. Let's keep moving. Okay, I took a picture. I think 8:25, not too bad, but I can't get too distracted anymore. Good distraction is good, but bad distraction can be time consuming and derail us from the main discussion topic. All right, so let's go back to our favorite topic of hybridization. I'm going to go through it fast. If you are feeling a little uncomfortable, go back and study, watch the previous video, look at the pictures. We can discuss it during office hours. Okay. I will show the hybridization of ethane just for the sake of it, because it'll help you kind of compare what's going on. So let me see what's the best way to do it. Let me do ethane here. You know what? Let's do it this way. You guys know what it looks like. This is ethane. Okay. Alkane. This is our alkane. And we will discuss alkene on this side. We'll discuss the double bonded version of ethane on that side. We are not discussing its name yet. Okay, you guys probably know what it's called. Let's say this is carbon 1 and carbon 2. Carbon 1 is excited state. Don't care about ground state anymore. 2s and 2p. Okay, undergoes sp3 hybridization, and C2 is the same way. 2s and 2p, okay, undergoes sp3 hybridization. 1, 2, 3, 4. This guy does the same thing. 1, 2, 3, 4. sp3, 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 and sp3, 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 and sp3. That almost sounds like a rhyme. 4 electrons, identical electrons in the tetrahedral shape. Okay, you're setting up the shape of tetrahedron the moment you go from this weird situation. 1, 2s, and 3 electrons are in 2p. They're different orbitals, but the bottom line is the molecule has very equivalent, very similar bonds. So they're probably mixing up and producing identical shape electrons in those 4 orbitals. Okay, sp3 orbitals. Then the bonding happens. The 4 hydrogens come. Hydrogen, another hydrogen, another hydrogen, and another hydrogen. So 4 hydrogens show up, and not 4 hydrogens, sorry, 6 hydrogens. 3 hydrogens and I'm thinking methane and I'm doing working on ethane. So 6 hydrogens show up and then they form the bond. So I can't really do it that way. So then they form ethane with this bond. Let's say, how do I show it? So yeah, let's do it this way. Hydrogen, hydrogen, hydrogen. Let's say that this is carbon 1 and carbon 2. Let's label them. Let's call them hydrogen A, B, and C, D, E, and F. Okay? So carbon 1 and carbon 2, they use 2 of their sp3 orbitals to make this sigma bond. So let's say, what shape shall I use? Let's say that those 2 orbitals form this bond. Make sense? So carbon 1 uses one of its sp3 orbital and carbon 2 uses one of its sp3 orbital to make this sigma bond. And then hydrogen A forms this bond. So this is that bond. Hydrogen B forms that bond. And hydrogen C forms this bond. You know what? Let's use color, like the way we did for our conformations. I think that will probably make things a little bit easier. D, E, and F. So that's already taken. Hydrogen D, hydrogen E, and hydrogen F. So this bond is that bond. This 2 electrons are forming that bond, and these 2 electrons are this bond. Make sense? Hydrogen E, hydrogen, oops, D, E, I need to relearn my alphabets. Hydrogen F. Okay? So this is what ethane looks like. All the bonds are sigma. They're all sigma bonds. Okay? I might ask you a trick question. I might say, how many sigma bonds and how many pi bonds are present in FN? That's a trick question. There is no pi bond, only sigma bonds. How many sigma bonds? Count. How many sigma bonds does FN have? Quick.
7.
7. 3, 3, and 1. Okay. All right. So we're done with the alkane guy. Now let's go to alkene. We discussed it. I'm going to go through it a little fast. Alkene, C1, C2, that has to go. And then we have four hydrogens. You know what? Let's put colors. Same way. We're just going to call it hydrogen A, hydrogen B, and we're going to call them hydrogen D and E. As if we lost C and F. Okay, we lost one from the left, one from the right. And then we have that sketchy bond. That's the pi bond, okay? Sigma, 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 and pi. Let's write down their electronic configurations again. Carbon 1, excited state. See, we are ignoring the ground state completely because that's walking backwards. You don't need to get stuck in the past. Carbon 1, and we are not drawing the core shell. 2s, 2px and 2py, and then I'm going to just draw this guy in red. 2pz, just to help you kind of use the color code to help you see through the molecule a little bit better. C2 star, the second carbon on the right side, 2s1, 2s2, 2p2, 2p, sorry, I don't know what I'm talking about. 2px1, 2py1, and 2pz. Okay? This is where you need to really concentrate. I know it's difficult to concentrate during the pandemic, but vaccinations are happening, vaccines are working, people are wearing more masks, behaving more like a civilized, reasonable, legitimate, logical person. So I think things are going to get better. Okay, so it's almost there. We are almost there. We can go around and start running around our neighborhood and saying hello to people pretty soon. Okay, so that's the deal. And there are four hydrogens, 2 attached to carbon 1, 2 attached to carbon 2. The bottom line is that this pi bond, sigma bond, happens by axial overlap of 2 orbitals. Pi bond happens by using pure p orbitals, side to side overlap. How does the p orbital look like? P orbital looks like, along the z-axis. Let's say this is the z-axis, right? So x, this is our convention, y, and z, right? So this is the z orbital, pz, 2pz, 2pz from carbon 1. Got it? That's the z orbital, right? It looks like this. So then we have, I just threw it away. I usually don't pick stuff from the trash. My mother told me not to do that. So that's one pz orbital, that's another pz orbital. Okay, that's one. And there is going to be another one. That's the dirty one. Carbon 2. So there is a second pz orbital. Let's say that's the Z direction. So they're like, there is one and there is one. So one here and one here, okay? And when the pi bond happens by lateral side to side overlap. It's not a great overlap. It's sketchy overlap. So when the overlap happens, there is overlap up here and there is overlap down here. Okay, and they end up making a little cloud here and a little cloud here. That's the pi bond. Okay, it's all mathematical equation. It's extremely dangerous. It's like the warning that comes in a child's play box. You're not supposed to be chewing on these toys or swallow it. Okay, because that there's a risk for choking to death, right? So this is what happens. So the bottom line is, when there is a double bond, and you know there is a pi bond, you need to keep aside two p orbitals. Don't touch them when you're trying to make chili. Okay, this chili is going to be having more beef than the beans. Okay, so these two orbitals are not touched. Save for the pi bond. Sounds like a slogan. Save for the pi bond. They go out in a procession in the periodic table. Save for the pi bond. Save for the pi bond. 314 is the pi day. Remember? Okay. You save that for the pi bond. That's those two pz orbitals, electrons, are used to make the pi bond. No hybridization business. They don't like hybridized electrons in the pi bond. They want pure p orbitals to make that side to side overlap. So what kind of mixing will happen here? Well, what are you left with? This is what you mix. For the blender to mix beef and chili, beef and bean, you are left with this. The hybridization is not going to be called sp3. It's going to be called what?
SP2.
sp2. It's going to be called sp2 hybridization. It's going to be called sp2 hybridization. So if you put 1s and 3p, you get 4 sp3 orbitals out of it. For this dude, how many hybridized sp2 orbitals should you produce by putting together one part of s and two parts of p? How many? Somebody else, not Michael. You put 3 pure orbitals. How many hybrid orbitals should you get out from the blender? How many bowls of chili?
3.
3. There you go. You get 3 sp2 orbitals. Each has an electron. I'm just using purple color to kind of make it stand out. Okay. And over here, the same deal. sp2, sp2, and sp2. This concept and this concept causes a lot of problem. Okay, that's why I'm kind of repeating what we went through. Okay, and 2pz has not been touched. Don't touch it. Can't touch that. Okay. Okay, so what's the deal now? Well, they need to use the hybrid orbitals to do all the sigma bonds. Okay, so that sigma bond, carbon 1 and carbon 2, use one of their hybridized electrons to make that sigma bond. That's that bond. Are we following? Is everyone following? It's getting a little convoluted. You need to stay focused. Get another cup of coffee. Don't let your cat or dog bother you right now. Stay focused. Now hydrogen A, that's this bond. Hydrogen B brings its 1s orbital electron, and that's that bond. Hydrogen D makes that bond. And hydrogen E makes that bond. I don't know how I'm going to draw it. What about these PZ orbitals? Well, the PZ and PZ, let's use a different color. How about green? PZ and PZ get together and then they form, well, obviously this bond. The two PZ orbitals make that pi bond. Got it? Take a look at it for like 30 seconds. I'm going to shut up and let you guys think about it. I don't remember which pen I picked up from the trash. Ah, darn it. Thank God my wife is not here right now. You guys really need to like sit down, watch the video repeatedly, maybe two times. If you're confused right now, I'm not going to go over it way too many times. We can discuss it during office hours, but then you guys need to get it in your system. It's very important that you understand. This is alkane. This is alkene. Okay, different kind of hybridization. This is sp3 and that's sp2. sp3 is putting 4 electrons and making 4 hybrid orbitals, identical. In sp2, you are making 3 identical electrons to make 3 sigma bonds, one between 2 carbons, one between carbon and hydrogen, and 3 pretty much the same way. The 2 carbons are using their unhybridized p orbitals to make the pi bond. Just simplify your concept. Keep those bullet points in your mind. Then I think it'll be fine. Take a look at the board. Please think. Try to think and try to understand what's going on. What's cooking here? Are we good? Okay. We have about half an hour left, and I want to really use this time for moving forward.
What would, I have a question, Doctor?
Yeah. Ray, go ahead.
What would be the, so can you explain the question in order for me to remember that this is what you're asking for? What would be the question again on that you would ask?
Let's continue the discussion, then we can have some like sample questions, like we can discuss like what I might be asking you from. We need to discuss a little bit more about the shape of it and stuff like that. So make sure you understand the concept so far. What is sp2 hybridization? When does sp2 hybridization happen? When you have a double bond, the 2 carbons at the end of the double bonds involved in the double bond business, they have sp2 hybridization. Why? Because you want to save a p orbital. That's why. Why do you need to save a p orbital? Well, to make the pi bond. What's the difference between pi and sigma bond? That could be a question. Sigma bonds happen by axial overlap. Pi bonds happen by side-to-side lateral overlap. Side-to-side overlap is this overlap, not this way. Okay, this is good. This is a strong bond. This is a sketchy bond about to cause divorce. We'll talk about the reactions of alkene, and you will see like how vulnerable the pi bond is. Okay, sigma bonds are really strong. Okay, That's all we have discussed. Want you to understand that, what we have discussed so far. sp2 hybridization. Why is sp2 called sp2? Students get lost, like completely lost and clueless in Clovis. So make sure that you are following the concepts, and you can compare the situation in an alkane and the situation in an alkene. Ane and ene, the different situation, sp3 and sp2. sp2, pz, pi bond. Connect the dots that way. You can write down some bullet points for your better understanding, simplify the concepts. However it works. But you guys need to really do that. Otherwise, it's going to cost you a lot of points in the near future, whenever the exams happen. Okay, let me erase it. Sometimes starting with a clean slate, clean canvas might be useful for better understanding.
I have a question, Dr. Maestro.
Yeah. Go ahead, Fernando.
Do all alkenes go under sp2 hybridization, or does it matter? Like, for example, if you did instead of ethane, if it was octane or pentane or something, would it be different?
Good question. Let's talk about it. Thank you. I always entertain questions, and I always feel more alive when you guys are participating. So thank you for asking questions, Ray and Fernando. And Keaton too. Yeah. I was telling my Chem 128A students, one of them has joined my research group. I'm not trying to recruit you guys, but if someone is feeling very comfortable with this course, and if you want to experiment something, doesn't matter. I'm not trying to distract you from your path. If you're an animal science major, plant science major, if you're a vet, or whatever it is, I'm not trying to screw up your future and make you miserable like me for the rest of your life. I'm not trying to do that. But if anybody is feeling like learning a little bit more how organic chemistry happens in the real lab setting, and if you're thinking about maybe try research for some time, if you're motivated, you don't have to have 4.0 GPS, GPA. I always have a soft corner for those who have made mistakes in the past, like I have, and then corrected it and gone up, made some career out of yourself by recognizing, acknowledging, and correcting your actions in the past. So if you want to give it a shot, let me know. Or there are lots of other fellow chemistry professors who are doing research. They're very kind and nice people. And so let me know if you think about it. Yeah, I probably have room for one person right now, starting later this semester or in summer. So we can discuss that. That doesn't mean that you have to change your major to chemistry. I've had biology majors. I have had a student who was a French and music major. I've had really weird people, like chemistry major and history minor, math major and chemistry minor, all kinds of, even high school students. So and I'm not trying to recruit, but I have room for one person. So, okay. All right. So talking about Fernando's question, methane, propane, ethane, and he mentioned octane. Okay, let's draw something crazy. Okay, alkanes, single bonded. Okay, I'm going to ask you a question. What's the hybridization here on carbon? Somebody spit it out.
sp3.
Be more confident. We say it with confidence. Okay. What's the hybridization here on ethane? Anybody?
sp3.
sp3. What do you think is the hybridization here in the middle of the propane molecule?
SP3.
sp3. What about here?
SP3.
sp3. What about here? sp3. Single bonded species, sp3. Okay, let's do something here. So if I ask you, what's the hybridization on this carbon? What's the answer?
SP2.
sp2. I just made a different species now. Listen carefully, somebody else who has not answered so far today. What's the hybridization at the end of this weird creature? Somebody else who has not talked today. What's the hybridization at the end, mouth of this worm? Somebody else, not Michael. I'm banning you. You're forbidden. Anybody else? Come on, wake up.
SP3.
sp3. What about here? Quick.
SP3.
sp3. What about here?
SP2.
Make sense, Fernando?
Yeah.
That's good. I'm glad that we clarified that. This is good. Very good. Yeah. Even cyclo species. What if I make this porcupine molecule? Hybridization here at the end of the methyl group. Fernando, what do you think?
SP3.
Excellent. Somebody else at this corner where the thorn grows.
SP3.
How about this guy? Anybody?
SP2.
You got it. I'm gonna post. I'm gonna take a picture and post it too.
So does it? I don't know if this might be right. I may be completely
No,
wrong, but
no.
I'm
You
kind of saying
don't,
if there's like a,
don't
I'm
think twice. Just say.
I'm trying to find if there's like a trend or something. So does it mean that the more bonds there is, the less orbitals that you can bond?
No,
I mean that you can hybridize?
You're making things complicated. Single bond. Do you see a double bond?
No.
Do you see anywhere there is a double bond? They're more substituted. Substitution has nothing to do with it. So what does this carbon look like? If I just draw this, if I expand it, right? So there is a carbon, that's the ring, that's carbon 1, 2, 3, 4, 5, right? That's a carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay, let's write down what else is going on here. Let's draw the hydrogens. CH3, CH3, CH3. No hydrogen here. There is a hydrogen here. Okay, so this carbon, okay, what does this carbon number 1 have to do? It has to produce 4 electrons pretty equivalent to make bonds with 4 carbons. So that's 1 electron, 2nd electron, 3rd electron, and 4th electron. So there is no double bond going on. So this shape has to be tetrahedral. If this shape has to be tetrahedral, then the hybridization must be sp3, because sp3 produces 4 identical sticks. 1, 2, 3, 4. That's the requirement. It has nothing to do with substitution, how busy that branching is. Unbranched, branch, doesn't matter. The bottom line is there is no double bond, only single bond. The key to your query should be, do I see any double bond? Is it all single bond? All single bond means sp3. sp3. This carbon needs to make 4 sigma bonds. It needs to make 1 sigma bond here, 1 sigma bond, another sigma bond, and another sigma bond. This is not going to be a perfect tetrahedral because it's got a carbon on one end and hydrogens on the other end. So it still needs to make 4 sticks pointed in a pretty tetrahedral shape. Therefore, this guy has to be sp3 as well. sp3 and sp3. If I ask you, what's the makeup of this particular bond? What is this particular sigma bond made out of? What kind of orbitals? What should be your answer? Anybody, somebody who has not answered today. What is this carbon 2, carbon 3 bond made out of? What kind of electrons, where are they sitting? What kind of locations they are in? Anybody? Anybody now?
SP3.
1. In order for you to make a bond, you need 2 electrons. So one guy is in sp3. What's the other one?
Well, if they're both carbons, they're both SP3.
What about this bond? What is that bond made out of? Somebody else, not Michael. What is this bond made out of? Carbon hydrogen bond, and the carbon is a single bonded carbon.
SP3, SP1,
sp3 and
SP1.
there is no sp1.
In
One
Correct here. Where is
One
this
is- yeah.
hydrogen's electron sitting in?
one is
1s.
Yeah.
Make sense? Too much organic chemistry? You guys want to take like a 15-second break and just scan the board and make sure you guys are okay? Let me draw this molecule one more time down here, showing all the carbons. Okay? If you can answer this, then you can answer pretty much everything. Okay. So Ray, your answer to your question. Questions that I might ask. I draw this molecule. Okay. I draw this molecule, maybe show all the hydrogens or not. I want everyone to think, and those of you who haven't answered today, I want you to inspire yourself, motivate yourself to answer. Look at the molecule very carefully. I've drawn it kind of big. First question. Ready? How many sigma bonds? Slow down, think, and answer. Those of you who haven't spoken today, I'm encouraging you to answer. How many sigma bonds?
Is it 9?
Don't ask, you answer. Be more confident, Trevin. 9 is Trevin says it's 9. Is that correct answer? Can somebody else check? Somebody else who hasn't spoken today. Trevin, thank you for answering. We will either boo you or cheer you, depending upon how your friends think about your answer.
I'll say 9. I'll second that.
Good teamwork. 9. Why? Sigma, sigma, 6 of them. Sigma, 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 3 of them, 9. How many pi bonds are present in the molecule?
1.
Really? That's it? Are you not being too conservative? I'm just messing with you. Who is this? Crystal. Anybody else wants to confirm or validate Crystal's answer? Only one pi bond, that's it? That sounds very sad. Anybody else? Speak up. Don't use any finger gesture or hand gesture or head wobbling or something with this.
I agree.
You agree? Okay, we agree. Thank you, Crystal. I was just messing with you. Yeah, you get that. Okay. Ray, you will be even happier now that we are continuing with more questions. Okay. I want another hour. Okay. Ready? Think. Don't give a knee-jerk answer. Don't be impulsive. Let's go to the easy one. What's the makeup of that CH bond? Think, analyze, answer carefully. If you have an answer today, I'll really encourage you to answer. What's that CH bond made out of? What kind of electrons are sitting in what kind of orbitals? Try to answer if you haven't spoken today. What orbital and what orbital?
The 1s and sp3.
And this is Desiree. It's a very small font. You said 1s and sp3. Clap or throw paper balls at Desiree. What should we do? Anybody else wants to validate? Somebody who hasn't talked today wants to validate Desiree's answer, plus thumbs up or thumbs down. There should be, Zoom should come up with a feature where we can throw things at each other. We were just talking about our in the pandemic situation in one of our faculty meetings maybe a couple of months ago, and I said Zoom should come up with an idea of bumping into each other, like it's going to be called Zoom bumping, and the thing will be like for a very short time you can crash someone else's Zoom meeting. You just show up and say, "Hey, how are you doing, man? I'm just saying hello," and then you will be automatically kicked out. So that's going to be called Zoom bumping. Okay, jokes apart. Don't encourage me to joke. Okay. Yeah, good or bad? Is that 1s and sp3? You got anybody wants to say something about it?
Good.
Good. Okay, awesome. Great. Thank you. Ready for the next one? Think. Don't give me a wrong answer. So there is pressure on you. This carbon and this carbon. What's the makeup of that bond?
sp3, sp3.
Who is this? Gabby? Yes, okay. You said sp3, sp3. We need the Zoom throwing feature right now. Paper ball throwing. Anybody else? Anybody wants to opine?
Isn't the bottom carbon sp2
Don't
hybridization?
ask. Make a statement, Michael.
Okay. Yeah, both of the bottom carbons are sp2 hybridized.
So you're saying this is right or wrong?
Wrong. Close.
You're being nice. Okay. So this bond should be. Gabs, you want to correct it? So this
Okay.
carbon, let's hold on. This is how you should proceed in the exam. What's this carbon's hybridization?
sp3.
sp3. What's this carbon's hybridization down here?
Oh, sp2.
sp2. What about this carbon's hybridization?
sp2.
sp2. In that case, what is this sigma bond made out of?
It would be sp2, sp3.
Yep.
Professor, I have a question.
Yes, ma'am. I'm
Um,
ready.
if you write the SP3 and SP2, if they're on the same together, do you put it in numerized situation like SP2 has to go first?
Doesn't matter.
Okay.
You can say, this is my son, John, and this is my son, I don't know, Joe. You can say John and Joe and Joe and John, doesn't matter.
Okay, Professor.
There's no order. Who knows? Okay, ready? We are doing review, that's fine. I'm trying to like pacify myself that we're doing review. That's fine. That's fine, Shantanu, just relax. We're having fun. That carbon and that hydrogen, what's that made out of?
SP2, SP3.
No!
Is it SP2 1S or 1S?
Louder, I can't hear you guys. You guys have no
1S,
breakfast or what? One more time.
1S and SP2.
Awesome. What about this bond, which is not a sigma bond? That's the pi bond. What's this pi bond made out of?
Carbon-carbon pi bond.
Yes, no, yeah, carbon-carbon pi bond. What is that carbon-carbon pi bonds make up?
2 p orbitals. So I guess we call it like PZ, PZ.
You can say 2p, 2p.
Okay.
2p or not 2p. Sorry, that was a bad joke. You guys read Shakespeare, I hope. That's what I meant. Okay, let's take a picture. This was plain and simple review. I want to talk about something before we close today, close our shop. Okay. We don't need this right now. I wanna clean up. We have roughly a minute. Okay, so let me use some models. So when we have I'm going to drop this. When we have 4 sp3, we're talking about sp3, single bond. When we have 4 sp3 orbitals, right? They shape like a tetrahedral. How does it look like? Like the cube. I wish I had a few more fingers. Definitely odd number of fingers. I don't want even number of fingers. Isha knows why. Okay, that's the shape. This is modeling. This is how the molecules like turn around. Front view, top view. Okay, tetrahedral, right? So when you have 4 sp3 hybridized orbitals, 1, 2, 3, and 4, this is the shape they take because they want to stay away from each other as far as possible. This is the best way they can. They're the farthest away from each other when the angle is 109.5, 109.5, 109.5, 109.5, everywhere 109.5. Okay, that's the deal. When you have in a double bond, right? Let's draw this double bond. That's the sp2 orbital, sp2 orbital, sp2, sp2 from carbon 2, sp2 from carbon 2, sp2 from carbon 2, and this is 1s from hydrogen 1, 2, 3, and 4, and 2pz, 2pz, okay? Sigma bond, sigma bond, sigma bond, sigma bond, sigma bond, and pi bond. Okay. Take a look at it for like 10 seconds and we'll go from there. Okay. We're going to continue discussion on Tuesday. So when we have 3 sp2 orbitals, remember the pi bond is this way, right? These are the 3 sp2 orbitals on xy plane because it has used 2px and 2py to make these hybrid orbitals. So they're on the x and y plane. This is the xy plane, this is the z plane. So this is pz, pz, side to side overlap, that's happening. When we have 3 sp2 orbitals, what should be their shape? Should they be planar? Should they have a shape like this? Should they look like a tripod? If they're planar, should they be 90 degrees and this one coming out from here, or 120 degrees between them? What makes sense to you that when you have 3 bar magnets connected to the North Pole in the center, what shape should they adopt? Should they be planar or not? First question, if they're planar, what should be the angle between them? There's no chemistry here, just common sense. What do you guys think? I'm dropping a hint. We're almost out of time. Let's answer that and you guys can go play. You can do your Zoom runarounds. You can do your Zoom.
I'd say planar and 120 degrees.
Planar and 120 degrees. There you go. So the bond angles, when you have a double bond, they're approximately 120 degrees. And the funny thing is that when you have 2 sets of sp2 orbitals, in order for you to keep the pi bonds parallel, this pi bond and this pi bond, these pi bonds must be parallel to do a really good, p orbitals must be parallel to do a really good pi bond, okay? If they're not perfectly parallel, this pi bond will be pretty sketchy. So if they are parallel, that means all the sp2, the 2 sets of sp2s, they must be planar. Okay? So when you have a double bond, around the double bond, these points, just listen to this and then we can drop the class. This point, this point, this point. So hydrogen 1, hydrogen 2, carbon 1, carbon 2, hydrogen 3 and hydrogen 4, this entire, this 6 atoms, okay? This is planar. 6 atoms on and around a double bond are, sorry, it's not writing very well, are planar. I'm upping my font size. Okay. So on and around the double bond, the 6 atoms on the double bond and whatever is attached, 4 things. Those 4 things and these 2 things, they are always planar. That's the shape around a double bond. Because otherwise, this pi bond will not be a pi bond. Because then you'll have to twist one side and it's not going to work out. Very important second observation. Single bonds can rotate, double bonds cannot rotate. or turn. Double bonds cannot turn. They're fixed in space. These four guys are always going to be parallel or planar. I think that's going to be it. I'm going to take a picture and I'll make things available as soon as I can. Have a good day, guys, and I'll see you. Have a good weekend. Huh, I didn't realize that we are almost there. Okay, I'm going to switch to the front camera, and I think there was a pretty heavy dose of chemistry today, so please study if you want to do well in this course. Please study and do well. I would love to give a lot of A's and B's and no C's, hopefully. 0 C's. Let's say there is going to be no C's this semester, no D's, no F's. How about that? Let's make it happen. You can do it. Only 23 of
Dr. Mitra,
Well, yeah.
are you gonna open up exam 1 to see what we got wrong?
Yes, I totally forgot. Yes, I'll do that right now. One second, hang on. Anybody else? Daniel, how are you? Did you ride your motorcycle today?
How you doing? I haven't yet, but I will. I'll get to it.
Okay, all right. How are you doing otherwise? Pretty good?
Yeah, we're good. We're doing all right.
Okay, excellent. Everybody else is doing well, I hope. Hang in there. Things are getting better. I think it's going to get much better, and we will see you guys coming week on Tuesday at 8 o'clock. Bye. Drinking coffee.
I kind of wanted to I guess elaborate on the question I asked earlier, Dr. Mitra.
Yeah, go ahead, Fernando.
So when I asked, kind of what I guess what I was asking, I think I asked it in the wrong way, was if there's like, when I was talking about a trend, it kind of seemed to me like there's like an inverse relationship between hybridization and the number of bonds. So for example, like when it was a single bond, then there was sp3, right? Because you're getting into the third orbital of that shell. When it was sp2, you're getting into the second orbital. For a triple bond, would it be you only go to the first orbital because you need the last two for the pi bonds, right?
You are thinking like a chemist, Fernando. You need to pick up a minor in chemistry. Yes. So well, this is. I'm not going to teach a new concept because most of you are not there. So Fernando, in a triple bond, think about a triple bond. Look at my hand, right? Bond 1, bond 2, bond 3. Okay. What do you think? How many of them are sigma and how many of them you think they're pi?
There's 2 pi's, right? 2 pi and 1 sigma?
Yep, there are 2 pi's. So in order to make 2 pi's, how many p orbitals do you need to save from
2?
each carbon? Yes. So what kind of hybridization will it be to make 2 sigma bonds? One here between the carbon and the hydrogen, and one here between the carbon 1 and carbon 2. You just need to make 2 hybridized orbitals. So what will be that hybridization called? sp3, sp. There you go, sp1. We don't say sp1, we call it sp. So that's how triple bonds happen. You are absolutely right. You're thinking.
But that's only for carbon, right? Like if you were doing it with another element, would it be different?
Oh, Fernando, what's your major?
Plant science.
Oh man, you're not doing justice to the universe. Yeah. No, I'm just kidding. You can stay as a plant scientist. I'm just kidding. It does apply to other elements too. Nitrogen, oxygen, things like that. Yeah, fluorine, it can happen that way. But once you go down to elements with d orbitals, all hell breaks loose. And then you need to talk to like one of the inorganic chemists, like my wife Kalyani or Dr. Attar or Dr. Goto or Masaki Uchida. And once it gets there, it gets very complicated because d orbitals are like me in my childhood, like extremely mischievous and unpredictable, and they can do anything that you don't predict. So they do funny business. So that bonding and all that becomes a nightmare for organic chemists. I can handle it. Yeah, but generally speaking, it does apply to other elements. Not all elements, but what we are usually dealing with, like a carbon, oxygen, carbon, nitrogen, oxygen. Yeah, it applies to those. But then things get more sketchy.
Some we probably won't be getting into that sort of stuff in this class.
We won't get into those. I don't think I will ever ask you about nitrogen's hybridization. I'm going to just stick to just carbon for this course. Yeah.
Well, that's probably not so bad then.
No, you can still sleep well. without any anxiety.
All right, thank you, Dr. Maitra.
All right, anybody else? Any other questions? You guys are doing well. Crystal, Willis, Matthew, Daniel, I already spoke. Judith, Cameron with a K, Sergio, Lupita, all good? All right, go play around. You can do your whatever you want to do on Zoom. I'm going to write to the Zoom CEO, see if we can add a feature, Zoom bumping.